All right. Good morning. Thank you, students, for being amazing examples of who you are, treating our sub with absolute respect. We should have a new packet, um, a new assignment sheet. If you haven't gotten those, let's get those out to you. And you're going to watch the video for notes for day 1, and you can start the sideline packet, provided I got that printed. Okay. So the sideline is due on Wednesday, 9:25. So you have a little while. Usually we have about a week, so it's a week and a couple days for you to finish that up. All right. So the pump up. Well, first of all, what we're doing today is we're going to define and identify examples and non-examples of rotation, reflection, and translation. So we're going to understand what those 3 things are. What we want you to do is look at the image below and think about what you notice. What math vocabulary can you see? What could you use to describe this? So take a minute, think about that. If you can go ahead and hit pause, that would be great. Thank you. All right, so hopefully you've had a few minutes to think about it. Some things you might have thought of are there's kind of a reflection. This half of the image looks just about like this half of the image, kind of a reflection. Maybe you saw some triangles, some symmetry. These are some good words. You may have identified some shapes that you saw, but there's definitely some reflection that this half and this half are reflections. And this is larger, this is smaller, smaller, so there's symmetry on either side. All right, hopefully you notice some of those things. All right, so go ahead, turn to this page in your packet, transformer. You see this little transformer up here? All right, we are talking about transformations. Motion in geometry. So geometric figures are often moved to create new, more complicated figures. This process of movement in geometry is called transformation, which is why we have our little transformer over there. Rigid transformation, rigid meaning doesn't change, rigid stays the same. So rigid transformation does not change the size or the shape of the object. So we didn't grow larger or smaller, we didn't change shape at all. The 3 types of rigid transformations are translation, reflection, and rotation. These are the 3 things that we're going to look at today. In each of the 3 rigid transformations, you'll be given a before figure called the pre-image. When you finish the transformation, the after figure is called the image. The image and the pre-image are congruent. So congruent means they have the same size, same shape. There was a transformation, it was a rigid transformation, right? They did not change size or shape, therefore they are congruent. And the symbol we use for congruent, we may have already talked about this, looks like an equal sign with a squiggly on top. All right, same size, same shape, that's what that means. All right, so the first one, we're looking at the examples and non-examples, so I want you to take a minute. I'm going to ask my sub, thank you so much, go ahead and hit pause, let the students discuss translation examples. So here's an example of translation, here's an example of translation. This is not translation, and this is not translation. So I want you to figure out what is translation. You can do a prediction of the definition, but why are these not translations? All right, go ahead, hit pause, and give students a few minutes to think about it. All right, so let's discuss. Hopefully you've already thought of these things. Here we are sliding. One way of talking about translation is a slide. Here we went straight down. So here we translated 1, 2, 3, 4, 5, 6 units to the right. Why did I say 6? I took A and I figured out how far. 1, 2, 3, 4, 5, 6. It moved 6 boxes to the right. So here it's A, here's A prime. Pre-image, image. So this is a translation, 6 units to the right. Here, translation down, I don't know, 6 inches. All right, why is this not a translation? Well, here this is kind of pointed up towards the right corner, and this one looks like it's pointed down towards the bottom corner. So in order for that to be a translation, it would have had to taken that same shape and slid down and still had that same upward pointing direction. Does anybody have the word for what happened here? Yes, exactly, that's the word. It's a reflection. Very good. All right, so this reflected over. All right, and over here, they have to be the same size, same shape, and they are the same shape, but they're not the same size. This was actually a dilation. It dilated, got larger. So that is not a translation. So our formal definition of translation, I'm going to put this up higher so you can all see it. When each point on a figure is moved the same distance, either vertically or horizontally. Notice we're not going in a diagonal. Okay, we're either talking about vertical or horizontal movement. All right, so go ahead and write that down. If you need to hit pause, you can. If students need more time, thank you. All right, so examples of translation, down 10 units, right 6 units. Now, I wouldn't say diagonal 15 units. I wouldn't say that, but I could say right 10 units, down 7 units, and that kind of is the same as a diagonal, but the way we describe it is two separate translations to the right and down, or down and then right. Really, the order doesn't matter in that sense. Okay, but notice the orientation hasn't changed. It's still pointing up, nothing's changed there. All right, we have another one, so take a minute. I'm going to go ahead and hit pause. Think about this. What is a reflection? What's important? Notice the ABCs, A prime, B prime, C prime. That little tick mark, A versus A prime, says this is my pre-image. This is where I started, and then my image is where I ended up. All right, so take a minute, think about that. Go ahead and hit pause. We want to make sure. Okay. Sorry. All right. Hopefully you guys had some time to talk. I apologize. I had some hints up here. I didn't mean these ones are not congruent, so they're not the same size or same shape. This is a translation. The orientation stayed the same. It moved up and over. But a reflection changes kind of the orientation of it. It reflects, every point reflects over a point. So over a line. When we reflect over the line. And it's important that we're identifying that line. We're going to do some fun stuff with that in the future. All right. But notice anything that was close to the line is still close to the line. It's just on the other side. Here it's far from the line. It's still far from the line. It's just on the other side, farther away on the other side. All right. So formal definition of a reflection is a rigid transformation. So size and shape does not change, in which a figure flips over a line of symmetry. And we must identify that line of symmetry. All right, I'm going to go ahead and move on. If you want to hit pause, more time for copying that down, go ahead. All right, so reflections, these are a little harder. So here, that would not be a reflection. In order to reflect, you need that to actually flip over, and I think we have transformations, and I can reflect in mirror in the X. So another way of thinking about it is mirroring, right? So I reflected over this line right here. If we identify that line, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here, y equals 12 is that line. I reflected over the line y equals 12. Okay, we could also reflect this way. If I reflect this way, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, here I reflected over the y-axis, which is actually, the y-axis is the same as the equation x equals 0, that line. All right, so here we're 5 units away. Here we're 5 units away. Sorry, I think I did one too many right there. Okay, All right. Cool. And the last one is rotation. So when we translate up or down, right or left. When we reflect, we always reflect over a line, and we need to identify that line. And when we rotate, we always rotate about a point. All right. But I want you to take a minute and look at these. Try to understand what is a rotation not. If you want to pause, go ahead. All right, we're going to start with a formal definition. A rigid transformation in which every point in a preimage turns around a point or a center of rotation. So sometimes that center of rotation is on the figure itself. So sometimes we say rotate about point A, and we rotate this figure around itself. But in this case, the center of rotation is outside of the figure. And if we look at this rotation, looks like it rotated 90 degrees. So it's important that, and we'll always specify like how far you want to rotate it. And we'll talk a lot more. We'll spend a whole day on rotations. But right now I just want you to see what is a rotation. Rotation is, notice it definitely changes the look of the shape, right? It can rotate around. Here we're rotating this point, rotated to this point. And every point is rotating the same amount. If I look at that angle, it's going to be the same. It looks like A rotated further just because it was further away, but it's still the same angle that it's rotating through. All right, and this is not a rotation because it's a reflection. These are not, they're reflected and translated. All right. So you have a couple examples. Where you're looking at grocery window, what would it look like on the inside? Try and draw that. What would you see if you saw it from the inside? It would look something like that, right? Some of you are a lot better at kind of visualizing this. And this one is always a challenge for students. It's kind of fun. Here we have some flags. So I'm standing behind 5 pupils who are signaling a 5-digit number to someone on the opposite side of the playground. From where I'm standing, the number looks like 2, 3, 4, 5, 6. What number is actually being signaled? So we're behind the people, so they're seeing this one. They're seeing this one as their first number. This one is their second, but I can tell you the number is not 6, 5, 4, 3, 2. That would not be the correct answer, right? Because we are seeing it from this way. They're seeing a different orientation depending on where they're looking. All right. That ends up being the number, but let's take a minute. So if you want to take a minute and think about it, that's awesome. This kind of explains. We took that image and reflected it, flipped it around. So what if we were starting with this one? If somebody understands what's going on and wants to come up and demonstrate that if you hold your arms in this direction, but then you turn around and face them, now it looks like a different number. It's kind of cool. All right. So this is your sideline packet. I did want to check in with you on this. So if you could get that out for a second. Okay, so just a really quick review on graphing lines. It says sketch the graph of each line, then state the x and y intercepts for each. All right, so here there's an equation, and we've talked about in the past y equals mx plus b. So our m, our slope, is 7/2. We rise 7, run 2, and -2 is our y-intercept. So the b is the y-intercept, and the m is the slope. All right, so -2 is our y-intercept, so 1, 2, -2, this is our y-axis. So we start here and we say, where's my y-intercept? Really, why are we plotting that point? What we're doing is we're saying, if x was 0, what would y be? If I plug a 0 right here, 0 times anything is 0. 0 minus 2 is negative 2. So 0, negative 2 is 1 point on that. All right, so then we use our slope, rise, and run. So we're going to go 1, 2, 3, 4, 5, 6, 7, run 2. There's a point. All we need is 2 points to make our line. Our lines continue forever. Okay, so again, y-intercept is 3, down 6 over 1. So down 3, down 6 over 1. That would be our line. Whoa, I missed my point a little. You want to be a little more accurate. All right, the other ones are in standard form. I would suggest you make a quick xy, plug in 0 for x, plug in 0 for y. You're just doing 2 ordered pairs. That's all you need is 2 points. Plug in 0 for x, 0 times 7 is 0, y equals 5. Plug in 0 for y. If y is 0, plus 0 equals 5. Divide by 7, and you get 5/7. Woo! Okay, that's a little tricky. But we're going to say 0, 1, 2, 3, 4, 5, and 5/7, 0. 5/7 would be almost 1 right here. Now, if somebody else has another way of graphing those quickly, please share with the class. That'd be awesome. All right. So we will talk a little more about this. You guys have some practice, so if you'll go ahead and start working on that, you have time to practice that. I will email my sub a Kahoot quiz in case they want to do it, but it's up to them. Okay. All right. Thank you for paying attention. Have a great day.